From a distance of 254 miles above the surface, Earth appears as a gentle arc of blues and whites against the darkness. This is the view from the International Space Station, where astronauts float past windows and watch continents drift beneath them in silence. The planet rotates slowly below, revealing patterns of light and shadow, ocean and land, cloud and clear sky. There is something profoundly calming about seeing Earth this way, as a single object suspended in space, with all its complexity visible, yet somehow simplified by distance. The atmosphere clings to the surface like a thin film. From orbit, it appears as a delicate blue band separating the solid planet from the void beyond. This narrow layer, just a few dozen miles thick compared to Earth's diameter of nearly 8,000 miles, contains everything we think of as weather. Every breath of wind, every drop of rain. It is thinner than the skin of an apple when scaled to the planet's size, yet, within this fragile envelope, all of Earth's life exists and persists. When you look at Earth from space, one of the first things that becomes clear is how much water defines its appearance. The oceans dominate the view. They cover 71% of the planet's surface, holding 97% of all Earth's water within their basins. These vast bodies of salt water appear in shades ranging from deep navy to turquoise, depending on depth, what lies beneath the surface, and how sunlight strikes the water at any given moment. The Pacific Ocean alone contains enough water to account for nearly half of all the water in Earth's global ocean, spreading across more than 60 million square miles. This is a journey through the quiet facts of Earth as seen from above. We'll move slowly through the details of what makes our planet visible and distinct from the perspective of space. There will be no urgency here, no dramatic revelations designed to startle. Instead, we'll simply observe what is known and measurable about Earth's atmosphere, its magnetic field, its water, its rotation, and the delicate systems that make it hospitable to life. You're welcome to listen actively, or to let these words wash over you as you rest. The information will unfold at a steady pace, with room to breathe between each idea. The planet beneath the International Space Station completes one full rotation every 23 hours, 56 minutes, and 4 seconds. This is called a sidereal day, measured against the background of distant stars rather than the sun. From the station's orbital vantage point, astronauts witness 15 sunrises and 15 sunsets in a single 24-hour period as they circle Earth once every 90 minutes at a speed of roughly 17,500 miles per hour. Yet, inside the station, everything feels still, weightless, and remarkably quiet despite the tremendous velocity. Let yourself settle into the rhythm of these observations. Earth's presence in space is not loud or insistent. It simply exists, turning steadily, wrapped in its protective layers, reflecting sunlight back into the cosmos. From any distance beyond a few thousand miles, the planet becomes a sphere of blue and white and brown and green, with swirling patterns of clouds that shift and change across its face. The view is both immense and intimate, both familiar and strange. We know this planet from the surface, from walking on its land and sailing on its seas, but seeing it whole, seeing it as one complete object, offers a different kind of knowing entirely. The atmosphere exists in layers, each with distinct characteristics determined by temperature, pressure, and chemical composition. The lowest layer, the troposphere, extends from Earth's surface to an altitude of about 7 to 10 miles, depending on latitude. It is thickest at the equator and thinner toward the poles. This is where all weather occurs, where clouds form, where rain falls, where winds blow. Between 75 and 80% of the atmosphere's total mass is concentrated in the troposphere, compressed close to the surface by Earth's gravity. The air we breathe consists of approximately 78% nitrogen and 21% oxygen by volume, with the remaining 1% composed of argon, carbon dioxide, water vapor, and trace amounts of other gases. This precise mixture has been shaped by billions of years of planetary processes, including volcanic outgassing, photosynthesis by living organisms, and chemical reactions in the atmosphere itself. The oxygen we depend on was not present in Earth's earliest atmosphere. It accumulated gradually over time, primarily through the metabolic activity of photosynthetic organisms that began transforming carbon dioxide and water into organic matter and oxygen more than 2 billion years ago. Above the troposphere lies the stratosphere, extending from about 10 miles to roughly 30 miles in altitude. Temperature increases with altitude in this layer, a reversal of the troposphere's cooling trend. This warming occurs because the stratosphere contains the ozone layer, where ozone molecules absorb ultraviolet radiation from the sun. This absorption protects life on Earth's surface from harmful UV rays that would otherwise damage DNA and make the surface far less hospitable to complex organisms. The ozone layer is most concentrated between 12 and 19 miles above the surface, though ozone molecules exist throughout the stratosphere in varying concentrations. The mesosphere extends from the stratosphere's upper boundary to about 53 miles above Earth's surface. Temperatures decrease again in this layer, reaching the coldest temperatures in Earth's atmosphere near the mesopause, the boundary between the mesosphere and the thermosphere above it. These temperatures can drop to negative 130 degrees Fahrenheit. The mesosphere is where most meteors burn up as they enter Earth's atmosphere, creating the bright streaks we call shooting stars. The atmospheric density is still sufficient here to create friction with incoming space debris, heating it to the point of vaporization. Beyond the mesosphere, the thermosphere extends from about 53 miles to between 300 and 600 miles in altitude, depending on solar activity. Temperatures rise dramatically in this layer, potentially reaching as high as 3,600 degrees Fahrenheit during periods of intense solar activity, though the air is so thin that this heat would not be felt as warmth in any conventional sense. The International Space Station orbits within the thermosphere, typically at an altitude around 254 miles. Despite the extreme temperatures, the station's exterior does not become unbearably hot because there are so few molecules present to transfer heat through collision. The outermost layer, the exosphere, blends gradually into space. It extends from the thermosphere's upper boundary to approximately 6,200 miles above Earth's surface, though there is no sharp dividing line between the exosphere and the vacuum of space beyond. In this region, atoms and molecules are so spread out that they can travel hundreds of miles without colliding with another particle. Some of these particles have enough energy to escape Earth's gravitational pull entirely, slowly leaking into space. Earth loses about 3 kilograms of hydrogen and 50 grams of helium every second through this process, though this loss rate is negligible compared to the planet's total atmospheric mass. The total mass of Earth's atmosphere is approximately 5.15 times 10 to the 18th power kilograms. To put this in perspective, if you could somehow gather all the air on Earth and compress it into liquid form, it would create a layer covering the planet's entire surface, to a depth of only about 34 feet. The atmosphere is simultaneously vast enough to contain all our weather and all the air we breathe, yet thin enough to be remarkably fragile when considered on a planetary scale. The Kármán line, located at an altitude of approximately 62 miles, is often used as the conventional boundary between Earth's atmosphere and outer space. This arbitrary designation was chosen because it represents the altitude above which the atmosphere becomes too thin to support aerodynamic flight. An aircraft would need to travel faster than orbital velocity to generate enough lift to stay aloft at this altitude, making traditional aviation impractical. Above this line, spacecraft rely entirely on orbital mechanics and reaction thrust rather than aerodynamic forces. From the International Space Station, the atmosphere appears as a thin blue line along Earth's horizon. When astronauts photograph sunsets from orbit, the sun's light passes through multiple atmospheric layers, each refracting light differently and creating distinct colored bands. The troposphere appears as a brownish or orange layer nearest the surface, colored by dust and aerosols. Above it, the stratosphere glows blue. Higher still, the mesosphere and thermosphere create fainter bands of violet and dark blue before fading into the blackness of space. These orbital sunsets and sunrises reveal the atmosphere's structure in a way that is impossible to observe from the ground. The atmosphere's protective function extends beyond shielding us from ultraviolet radiation and burning up meteors. It also moderates temperature extremes. Without an atmosphere, Earth's surface would experience temperature swings similar to those on the Moon, which vary from -208 degrees Fahrenheit during the lunar night to 250 degrees Fahrenheit in direct sunlight. The atmosphere absorbs and redistributes heat through convection and the water cycle, maintaining relatively stable temperatures that allow liquid water to exist at the surface and life to persist in a wide range of environments. The greenhouse effect, driven by trace gases including carbon dioxide, methane, and water vapor, traps some of the infrared radiation emitted by Earth's surface, warming the planet by approximately 59 degrees Fahrenheit compared to what its temperature would be without this effect. This natural greenhouse effect is essential to maintaining conditions suitable for life as we know it. Water vapor is actually the most significant greenhouse gas by volume, though its concentration in the atmosphere varies considerably depending on temperature and location, ranging from nearly 0% in cold, dry regions to more than 4% in warm, humid areas. Atmospheric pressure at sea level averages approximately 101,325 pascals, or about 14.7 pounds per square inch. This pressure is the result of the weight of all the air above any given point pressing down due to gravity's pull. Pressure decreases exponentially with altitude as the amount of overlying air decreases. At the cruising altitude of commercial airliners, around 6 to 7 miles above sea level, the pressure is only about 1/3 of the sea level value. At the peak of Mount Everest, 8,848 meters above sea level, the pressure is roughly 1/3 of sea level pressure, making breathing difficult without supplemental oxygen. The atmosphere is not static. It moves constantly, driven by uneven heating of Earth's surface by the sun. Warm air near the equator rises, creating regions of low pressure. This air moves poleward at high altitudes, cools, and descends around 30 degrees latitude north and south, creating subtropical high-pressure zones. These circulation patterns, combined with Earth's rotation, create the prevailing wind patterns that sailors and meteorologists have mapped for centuries. The trade winds blow from the northeast in the northern hemisphere and from the southeast in the southern hemisphere, converging near the equator in a region known as the Intertropical Convergence Zone. From orbit, you can observe these atmospheric circulation patterns through cloud formations. The long bands of clouds that spiral around mid-latitude storm systems reveal the jet stream, a high-altitude river of air flowing at speeds that can exceed 200 miles per hour. The jet stream's position and strength influence weather patterns across entire continents. steering storms, and determining whether a region will experience warm or cool temperatures. Its meandering path is visible from space as a series of ridges and troughs in the cloud patterns that follow its flow. The atmosphere protects us so thoroughly that we rarely consider what space beyond it is like. The vacuum of space is not truly empty, but the density of particles is so low as to be nearly negligible. In interplanetary space, there might be only a few particles per cubic centimeter, compared to about 10 to the 19th power molecules per cubic centimeter in the air at sea level. This difference is so extreme that it challenges comprehension. The atmosphere, thin as it appears from space, represents an almost inconceivably dense concentration of matter compared to the surrounding cosmic void. Earth possesses a magnetic field that extends far beyond the atmosphere, creating a protective region called the magnetosphere. This invisible shield deflects most of the solar wind, a continuous stream of charged particles ejected from the sun's outer atmosphere. Without this magnetic protection, the solar wind would gradually strip away Earth's atmosphere, much as it appears to have done to Mars after that planet's magnetic field weakened billions of years ago. The magnetic field is generated deep within Earth's interior, in the outer core, approximately 1,800 miles beneath the surface. Here, molten iron and nickel flow in convective currents driven by heat, escaping from the even deeper inner core. The movement of this electrically conductive liquid metal generates electric currents, which in turn produce magnetic fields. This self-sustaining process is called the geodynamo, and it has operated for at least 3.45 billion years, possibly longer. At Earth's surface, the magnetic field strength ranges from approximately 25 to 65 microteslas, depending on location. The field is strongest near the magnetic poles and weakest near the magnetic equator. For comparison, a typical refrigerator magnet has a field strength of about 5,000 microteslas, roughly 100 times stronger than Earth's field at the surface. Despite its relative weakness, Earth's magnetic field extends thousands of miles into space, far enough to create a substantial barrier against the solar wind. The magnetosphere can be visualized as a bullet-shaped magnetic bubble surrounding Earth. On the side facing the Sun, the solar wind compresses the magnetosphere to a distance of approximately 39,000 miles from Earth's surface, though this distance varies considerably depending on the intensity of the solar wind. During normal conditions, the day-side magnetopause, the outer boundary of the magnetosphere, sits at about 630,000 kilometers, or roughly 63,000 miles from Earth. During intense solar storms, when coronal mass ejections from the Sun slam into Earth's magnetic field, the magnetopause can be pushed significantly closer to the planet, sometimes to within 30,000 miles of the surface. On the night side, away from the Sun, the magnetosphere is stretched into a long tail called the magnetotail, which extends more than 300,000 miles downstream in the direction opposite the Sun. This tail is created by the solar wind flowing past Earth, much like water flowing past a rock in a stream creates a wake. The magnetotail stores magnetic energy and can release it explosively during geomagnetic storms, creating auroras and potentially disrupting satellites and power grids on Earth's surface. The solar wind itself is a fascinating phenomenon. The Sun constantly ejects charged particles, primarily electrons and protons, from its outermost atmosphere at speeds ranging from about 250 to 500 miles per second. This wind would strip away Earth's atmosphere in a matter of millions to tens of millions of years if the magnetic field did not deflect it. The magnetosphere channels most of these particles around Earth, creating a protected cavity within which our planet resides. However, the magnetosphere is not perfectly sealed. There are two weak points above the north and south magnetic poles, regions called the polar cusps. Here, the magnetic field lines point more directly toward Earth's surface rather than running parallel to it, creating funnels through which solar wind particles can leak into the upper atmosphere. When these charged particles collide with oxygen and nitrogen molecules in the thermosphere and mesosphere, they transfer energy to those atmospheric molecules, causing them to emit light. This is how auroras form. The aurora borealis in the northern hemisphere and aurora australis in the southern hemisphere typically occur in oval bands centered on the magnetic poles, extending to latitudes of about 60 to 75 degrees. During intense geomagnetic storms, when the sun ejects particularly powerful bursts of plasma toward Earth, the aurora ovals can expand significantly, bringing the lights to much lower latitudes. Historical records describe auroras being visible from the Caribbean and other tropical regions during the most extreme solar storms. The colors of auroras depend on which atmospheric gases are being excited and at what altitude the collisions occur. The most common color is green, produced by oxygen molecules at altitudes of about 60 to 150 miles. Red auroras, less common, are produced by oxygen at higher altitudes, above 150 miles, where the atmosphere is thinner and collisions occur less frequently. Blue and purple auroras are produced by nitrogen molecules and typically appear at lower edges of aurora displays. From the International Space Station, which orbits at an altitude of about 254 miles, astronauts sometimes find themselves inside the aurora, with the shimmering curtains of light extending below the station toward Earth's surface. The magnetic field's orientation and strength are not constant. The magnetic poles wander slowly across Earth's surface. The North Magnetic Pole, currently located in the Canadian Arctic, has been moving at an accelerating pace over the past few decades, traveling at speeds of about 30 to 40 miles per year. This movement is caused by changes in the flow patterns of molten iron in the outer core, which are still not fully understood despite decades of study. More dramatically, the magnetic field occasionally reverses its polarity entirely, with the north and south magnetic poles switching places. These reversals have occurred hundreds of times throughout Earth's history, at irregular intervals averaging several 100,000 years between events. The last reversal occurred approximately 780,000 years ago. We know about these ancient reversals because certain minerals in rocks, particularly iron-rich minerals in volcanic lava, align themselves with Earth's magnetic field as the lava cools and solidifies. By studying the magnetic orientation preserved in rocks of different ages, geologists can reconstruct the history of Earth's magnetic field over hundreds of millions of years. During a reversal, which can take anywhere from 1,000 to 10,000 years to complete, the magnetic field does not disappear entirely, but it may weaken significantly and become more complex, with multiple magnetic poles existing simultaneously. Some scientists have speculated that the current weakening of the magnetic field, which has declined by about 6% per century over the past few centuries, might indicate an approaching reversal, though this remains uncertain. The field's strength is currently within its normal range of variability over the past several thousand years, and temporary weakenings have occurred many times without leading to full reversals. One region where the magnetic field is particularly weak is called the South Atlantic Anomaly, a large area extending from South America into the southern Atlantic Ocean where the magnetic field strength is significantly lower than expected. This anomaly is not static. It is expanding westward and continuing to weaken. In this region, satellites experience higher rates of damage from radiation because the protective magnetic field is weaker, allowing more high-energy particles to penetrate closer to Earth's surface. The anomaly's origin appears to be related to the structure of Earth's core and the dynamics of the geodynamo, but its exact cause remains an active area of research. The magnetosphere also creates radiation belts, regions where charged particles become trapped in Earth's magnetic field. These Van Allen radiation belts, named after physicist James Van Allen, who discovered them in 1958, consist primarily of energetic electrons and protons that spiral along magnetic field lines, bouncing between the north and south magnetic poles. The inner belt extends from about 600 to 3,700 miles above Earth's surface, while the outer belt ranges from about 9,300 to 15,500 miles. Between these two belts is a slot region where particle densities are much lower. These belts pose a radiation hazard to satellites and astronauts traveling beyond low Earth orbit, requiring careful mission planning and shielding. Earth's magnetic field is quiet and constant from our perspective on the surface. We are vaguely aware that compasses point north because of it, but we do not perceive the vast, invisible shield surrounding our planet, deflecting deadly radiation every moment of every day. From space, this shield is equally invisible, detectable only through its effects. The auroras that dance along the polar regions, the way solar plasma flows around our planet, like water around a stone. The protection that allows our thin atmosphere to persist despite the constant solar wind. When astronauts from the Apollo 17 mission looked back at Earth from a distance of 28,000 miles on December 7, 1972, they photographed the planet fully illuminated by the sun, with Africa and the Antarctic ice sheet prominently visible. This image, which became known as the blue marble, revealed Earth as it truly appears from deep space, a planet dominated by water. The blue of the oceans, the white of clouds and ice, these colors define Earth's appearance in a way that no other combination could. 71% of Earth's surface is covered by ocean. This water is not distributed evenly across the globe. The southern hemisphere is dominated by ocean, with 81% of its surface covered by water, while in the northern hemisphere, only 61% of the surface is ocean. If you could stand at a point in the South Pacific Ocean near New Zealand and look around in all directions, you would see more ocean visible from that single vantage point than from any other location on Earth. This point, known as the oceanic pole of inaccessibility, is farther from land than any other spot on the planet's surface. The Pacific Ocean alone covers more than 30% of Earth's entire surface, an area larger than all the land on the planet combined. It contains approximately 723 million cubic kilometers of water, more than all other oceans combined. If you could somehow gather all of Earth's continents and place them in the Pacific, there would still be room left over. The ocean's average depth is about 3,800 meters, or approximately 12,500 feet, though in the deepest trenches it plunges to more than 10,900 meters, nearly 7 miles below sea level. The deepest known point in the ocean is the Challenger Deep in the Mariana Trench, which extends to a depth of approximately 10,920 meters, or about 36,200 feet. At this depth, the pressure is more than 1,000 times greater than atmospheric pressure at sea level, approximately 8 tons per square inch. Only specially designed vehicles can survive such pressures. For comparison, Mount Everest, the highest point on land, reaches 8,848 meters above sea level. If you could place Everest at the bottom of the Challenger Deep, more than 2,000 meters of water would still cover its peak. Earth's oceans hold approximately 96.5% of all the water on the planet. The remaining 3.5% is fresh water, and most of that is locked away in glaciers and ice caps, particularly in Antarctica and Greenland. Glaciers and permanent snow cover contain about 68.7% of Earth's fresh water. Another 30.1% is stored underground as groundwater. Less than 1% of Earth's fresh water is found in lakes, rivers, soil moisture, the atmosphere, and living organisms combined. If you could somehow take all of Earth's water and form it into a sphere, that sphere would have a diameter of about 860 miles, roughly the distance from Salt Lake City to Topeka, Kansas. It would look surprisingly small next to the planet itself. Yet, this relatively modest amount of water is essential to everything we know about Earth's habitability and climate. Water's unique properties, its high heat capacity, its ability to dissolve many substances, its expansion upon freezing, its liquid state at the temperatures common on Earth's surface, all of these characteristics shape our planet's systems in fundamental ways. The ocean is not a single uniform body of water. It varies in temperature from approximately -2 degrees Celsius in polar regions, where seawater can remain liquid below the freezing point of pure water due to its salt content, to more than 30 degrees Celsius in tropical surface waters. Salinity varies as well, from about 33 parts per thousand in regions where river input dilutes the ocean to more than 40 parts per thousand in areas of high evaporation like the Red Sea. These variations in temperature and salinity drive ocean currents, which transport heat around the globe and influence climate on every continent. The ocean absorbs heat from the sun, particularly in the tropics where solar radiation is most intense. This heat is then redistributed by ocean currents. The Gulf Stream, for instance, carries warm water from the Gulf of Mexico across the Atlantic toward Europe, releasing heat to the atmosphere along the way and moderating temperatures in Western Europe. Without this heat transport, countries like Britain and Ireland would have climates more similar to Newfoundland or Labrador, which lie at the same latitudes but experience much harsher winters due to the absence of warm ocean currents offshore. From orbit, ocean currents are not directly visible, but their effects are. The boundaries between water masses of different temperatures create subtle variations in sea surface height that can be detected by satellite altimeters. Warm water expands slightly and creates subtle bulges in the ocean surface, while cool water contracts and creates slight depressions. These differences, though measured in centimeters, reveal the large-scale circulation patterns that govern ocean dynamics. Clouds also reveal ocean processes when viewed from space. In regions where cold, nutrient-rich water upwells from the deep ocean to the surface, the cooler sea surface temperatures can influence cloud formation patterns. The atmospheric circulation itself is partly driven by the temperature differences between ocean and land, creating monsoon patterns, sea breezes, and the formation of tropical cyclones over warm ocean waters. The ocean surface from space appears remarkably smooth in some areas and textured in others. Where winds are calm, the water can be mirror-like, reflecting sunlight in a concentrated bright patch called sun glint. Where winds are strong, the surface becomes rougher, scattering sunlight in many directions and appearing darker. Satellites use these reflectance patterns to map wind speeds across the global ocean, creating detailed pictures of how energy moves through the ocean atmosphere system. Near coastlines, the ocean's color changes dramatically. The deep blue of open ocean gives way to lighter blues and greens in shallow water where sunlight reflects off the seafloor. River discharge creates plumes of sediment-laden brown or green water extending miles offshore. These sediment plumes are visible from the International Space Station, showing where rivers like the Amazon and the Mississippi carry dissolved minerals and organic material from continents into the ocean. These nutrients support vast populations of phytoplankton, microscopic photosynthetic organisms that form the base of the ocean food web and produce approximately 50% of the oxygen in Earth's atmosphere. Phytoplankton blooms can be seen from space as swirls of green and turquoise in areas where nutrient-rich water supports rapid algae growth. These blooms are most common in the North Atlantic during spring and in the Southern Ocean during the Antarctic summer. The color comes from chlorophyll, the pigment that captures sunlight for photosynthesis. In particularly dense blooms, the ocean can appear almost neon green, a startling contrast to the dark blue of surrounding waters. Ice covers portions of the ocean in polar regions, and this ice is constantly changing. Sea ice in the Arctic Ocean expands each winter and contracts each summer, following a seasonal cycle that has persisted for millennia. In winter, Arctic sea ice can cover an area of about 15 million square kilometers. In summer, it shrinks to roughly 5 million square kilometers, though these numbers have been changing in recent decades. The sea ice is never still. It drifts with winds and currents, breaking into leads, pressure ridges, and polynias, areas of open water surrounded by ice. Antarctic sea ice follows a similar seasonal cycle, but in the opposite phase, expanding during the southern hemisphere winter and contracting during summer. The Antarctic ice sheet itself, the continent-sized mass of ice covering Antarctica, is distinct from sea ice. This ice sheet contains about 26.5 million cubic kilometers of ice, roughly 90% of all the ice on Earth, and about 68% of all fresh water. If all of this ice were to melt, which would take thousands of years under any realistic scenario, global sea levels would rise by approximately 58 meters, or about 190 feet. The water cycle connects the ocean to the atmosphere and land in an endless circulation. Water evaporates from the ocean's surface, particularly in warm, dry regions like the subtropics. This vapor rises into the atmosphere, where it can be transported thousands of miles by winds before condensing into clouds and falling as precipitation. About 78% of all precipitation falls over the ocean, while the remaining 22% falls on land. Of the precipitation that falls on land, some flows back to the ocean through rivers, some infiltrates into groundwater, and some evaporates back into the atmosphere. The amount of water in the atmosphere at any given time is relatively small, only about 12,900 cubic kilometers, or roughly 1/10,000% of all water on Earth. Yet this atmospheric water is constantly cycling through the system, with water molecules spending an average of only about 9 days in the atmosphere before returning to the surface as precipitation. This rapid turnover means the entire atmospheric water content is replaced roughly 40 times per year, creating the continuous cycle of evaporation, transport, condensation, and precipitation that drives weather and sustains life on land. From the International Space Station, astronauts can watch this water cycle in action. They see clouds forming over tropical oceans as warm, moist air rises and cools. They see river systems carrying water back to the sea, their braided channels and deltas visible in intricate detail. They see snow covering mountain ranges and ice sheets blanketing polar regions. They see it all as one interconnected system, water moving endlessly between ocean, atmosphere, and land in a cycle that has persisted for billions of years and will continue as long as Earth retains its liquid water and moderate temperatures. Clouds cover approximately 70% of Earth's surface at any given moment. They are not distributed evenly. The intertropical convergence zone, where trade winds from the northern and southern hemispheres meet near the equator, is almost constantly cloudy. Rising warm, moist air creates towering cumulonimbus clouds and frequent thunderstorms. In contrast, the subtropical high-pressure zones around 30 degrees north and south latitude are characterized by descending dry air and relatively clear skies, creating the world's major desert regions, including the Sahara, the Australian outback, and the southwestern United States. From space, cloud patterns reveal atmospheric dynamics in beautiful detail. Bands of clouds spiraling around low-pressure systems trace the movement of fronts and the circulation of air around storm centers. In the northern hemisphere, these systems rotate counterclockwise, while in the southern hemisphere, they rotate clockwise, a consequence of Earth's rotation and the Coriolis effect. The comma-shaped cloud patterns associated with mid-latitude cyclones are instantly recognizable from orbit, their characteristic shapes mapping the interplay of warm and cold air masses. Tropical cyclones, known as hurricanes in the Atlantic and Eastern Pacific, and typhoons in the Western Pacific, appear as spiraling disks of clouds with clear eyes at their centers. These massive storm systems can span hundreds of miles in diameter, with eye diameters ranging from a few miles to more than 60 miles across. The eye wall, the ring of clouds immediately surrounding the eye, contains the strongest winds and most intense rainfall in the storm. From the International Space Station, astronauts have photographed these systems and reported being able to see down through the eye to the ocean surface below, a strange island of calm amid the surrounding violence. Cloud types are determined by altitude and atmospheric conditions. High-altitude cirrus clouds, composed of ice crystals, form at altitudes above 20,000 feet and often appear as wispy streaks across the sky. These clouds are so thin that they cast little shadow and allow sunlight to pass through, though they can create halos around the sun or moon when light refracts through their ice crystals. From space, extensive cirrus cloud fields appear as faint veils partially obscuring the features below. Mid-level clouds, including altocumulus and altostratus, form between 6,000 and 20,000 feet. These clouds can create uniform, gray overcast conditions or appear as groups of small, rounded elements that create a textured appearance when viewed from above. The altocumulus castellanus variety, with its tower-like projections, often indicates atmospheric instability and can precede the development of thunderstorms later in the day. Low clouds, below 6,000 feet, include stratus, stratocumulus, and cumulus varieties. Stratus clouds create uniform gray layers that can persist for days, particularly in coastal regions where marine layers of cool, moist air spread inland. Stratocumulus clouds appear as groups or layers of low, rounded clouds with visible gaps between them. Cumulus clouds, the puffy, cotton-like clouds of fair weather, form when rising air currents cool and moisture condenses, creating clouds with flat bases at the condensation level and rounded tops that extend upward where rising air continues to rise and condense. Cumulonimbus clouds, the towering giants that produce thunderstorms, extend from low altitudes all the way to the tropopause, the boundary between the troposphere and stratosphere. These clouds can reach heights of 40,000 to 60,000 feet or more, creating anvil-shaped tops as rising air spreads out horizontally when it reaches the stable stratosphere and can rise no further. Lightning flashes within these clouds as electrical charges separate, with positively charged ice crystals rising to the cloud tops and negatively charged particles concentrating lower in the cloud. The discharge between these regions creates the brilliant flashes visible for dozens of miles, even hundreds of miles, when viewed from orbit at night. From the International Space Station, astronauts sometimes witness thunderstorms from above, seeing the tops of cumulonimbus clouds illuminated from within by lightning flashes. These flashes occur dozens or even hundreds of times per minute in the most intense storms, creating a nearly constant flickering visible through the cloud tops. The view is surreal, watching energy release on such a massive scale from the safety of orbit, with no sound, no turbulence, just the silent display of atmospheric electricity. Clouds interact with radiation in complex ways that influence Earth's climate. They reflect incoming solar radiation back to space, cooling the surface below. This effect is strongest for low, thick clouds like stratocumulus, which can reflect more than 60% of incoming sunlight. At the same time, all clouds absorb and emit infrared radiation, trapping heat like a blanket and warming the surface below. This greenhouse effect is strongest for high, thin cirrus clouds. The net effect of clouds on Earth's climate is cooling, as the reflection of solar radiation outweighs the trapping of infrared heat. Without clouds, Earth's surface would be significantly warmer and the distribution of water would be dramatically different. The water cycle continues endlessly, driven by energy from the sun. Each day, approximately 1,400 cubic kilometers of water evaporates from the ocean's surface and land, rising into the atmosphere. Nearly the same amount falls back as precipitation, maintaining a rough balance over time. This cycling connects the ocean, atmosphere, and land in a continuous exchange of water molecules that have been circulating for billions of years. The water molecule you drink today may have fallen as rain over ancient forests, flowed through prehistoric rivers, been absorbed by dinosaurs, or drifted in clouds above oceans that no longer exist in their ancient configurations. From space, these processes appear almost impossibly delicate. The narrow band of atmosphere, the precise temperature range that allows liquid water, the constant cycling between states of matter, all of this occurs within a thin shell around a rocky planet. Yet, this system has persisted for eons, maintaining conditions suitable for life through countless changes in solar output, volcanic eruptions, asteroid impacts, and the gradual evolution of the atmosphere itself. The view from orbit makes Earth's habitability seem both miraculous and fragile, a unique set of conditions that has allowed complexity to emerge and persist. Earth rotates on its axis once every 23 hours, 56 minutes, and 4.09 seconds. This is called a sidereal day, measured relative to the distant stars rather than the sun. A solar day, the time from one noon to the next as measured by the sun's position in the sky, is slightly longer at 24 hours. The difference arises because Earth is also moving along its orbit around the sun, so it must rotate slightly more than 360 degrees for the sun to return to the same position in the sky. At the equator, Earth's surface moves at approximately 1,040 miles per hour due to this rotation. This speed decreases with latitude. At 45 degrees north or south, the surface speed is about 733 miles per hour. At the poles, there is essentially no rotational speed, as those points sit directly on the axis of rotation. We do not feel this motion because everything around us, the air, the ground, everything moves together with the same rotational velocity. The rotation creates the Coriolis effect, an apparent deflection of moving objects when viewed from Earth's rotating reference frame. In the northern hemisphere, moving objects appear to curve to the right. In the southern hemisphere, they curve to the left. This effect is zero at the equator and strongest at the poles. It influences the circulation of the atmosphere and ocean, causing weather systems to rotate counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. It also affects the paths of long-range missiles, the flight of aircraft, and even the trajectory of thrown objects over sufficiently long distances, though the effect is negligible for most everyday activities. From the International Space Station, which orbits in the same direction as Earth's rotation, the planet appears to drift slowly backward beneath the spacecraft. The station completes one orbit every 90 minutes, moving at roughly 17,500 miles per hour, while Earth rotates beneath it at a much slower pace. This creates a complex dance where the station passes over different parts of the planet with each orbit, tracing a ground track that gradually shifts westward. The rotation axis is not perfectly perpendicular to Earth's orbital plane. Instead, it is tilted at an angle of approximately 23.4 degrees from the perpendicular. This tilt is called obliquity, and it is responsible for the seasons. As Earth orbits the Sun, different hemispheres receive more direct sunlight at different times of year. When the northern hemisphere is tilted toward the Sun, it experiences summer with longer days and more direct sunlight. Simultaneously, the southern hemisphere is tilted away from the Sun and experiences winter with shorter days and less direct sunlight. 6 months later, the situation reverses. The tilt remains nearly constant in direction as Earth orbits the Sun, a phenomenon called axial parallelism. Earth's north pole consistently points toward the star Polaris, which we call the North Star, though this alignment is not perfect and changes very slowly over thousands of years due to a wobble in Earth's rotation called axial precession. This wobble takes approximately 26,000 years to complete one cycle, causing the direction of Earth's axis to trace a slow circle against the background of stars. In 13,000 years, Earth's north pole will point toward the star Vega instead of Polaris. The obliquity itself is not constant over very long timescales. It varies between approximately 22.1 and 24.5 degrees over a cycle lasting roughly 41,000 years. This variation is caused by gravitational interactions with other planets and the Moon. Currently, the obliquity is about 23.4 degrees and is slowly decreasing. A larger obliquity creates more extreme seasons, with hotter summers and colder winters. A smaller obliquity creates milder seasons. These changes in obliquity are thought to play a role in triggering ice ages, as milder summers at high latitudes allow snow and ice to persist year-round, gradually building into massive ice sheets. The rotation rate is also not perfectly constant. Tidal forces from the Moon gradually slow Earth's rotation, lengthening the day by approximately 1.7 milliseconds per century. This is a tiny change, imperceptible over human lifetimes, but it accumulates over geological time. When Earth first formed approximately 4.54 billion years ago, a day was only about 6 hours long. The Moon was also much closer to Earth then, and tides were far more extreme than they are today. From space, Earth's rotation is most visible during the day-night transition. As the Terminator, the line dividing daylight from darkness, sweeps across the surface, you can watch cities light up as they enter night and see how the distribution of human settlement follows coastlines, river valleys, and favorable terrain. The lights reveal population density and economic activity in ways that are invisible during daylight. Major metropolitan areas appear as bright blobs of yellow-white light. Road networks appear as bright lines connecting cities. Rural areas remain dark, with only scattered points of light marking small towns and isolated settlements. The view of Earth at night from the International Space Station offers a different perspective than satellite images. The station's orbit carries it over different latitudes, providing oblique views that show the curvature of Earth and the airglow layer that extends above the surface. Airglow is a faint emission of light by the atmosphere, caused by various chemical reactions and energy absorption processes in the upper atmosphere. It appears as a thin greenish or reddish band along the horizon when viewed from orbit, extending from about 50 to 400 miles above the surface. During the day, sunlight dominates and air glow is invisible, but at night it becomes apparent, creating an ethereal glow that separates the dark surface from the darkness of space. The colors depend on which atoms and molecules are emitting light. Green air glow is typically caused by oxygen atoms recombining into oxygen molecules at altitudes around 100 to 300 kilometers. Red air glow can be caused by oxygen at higher altitudes or by other processes. Sodium from meteors burning up in the atmosphere can create yellow air glow. These emissions are far fainter than the bright city lights below, but they are constant and reveal the ongoing chemical and physical processes in the upper atmosphere. From orbit, you can also see lightning illuminating clouds from within, like a lamp inside a paper lantern. Thunderstorms become visible as bright patches of flickering light scattered across the dark continents and oceans. Some lightning travels upward into the atmosphere, creating exotic phenomena like sprites, which are brief, dim flashes of red light that extend tens of miles above the cloud tops, or blue jets, which shoot upward from the tops of thunderstorms. These upper atmospheric electrical discharges are invisible from the ground, but are occasionally captured by astronauts photographing thunderstorms from above. The rotation continues unchanging, as it has for billions of years. Day follows day in an endless cycle. From space, this rotation appears smooth and inevitable, a fundamental property of the planet. The 24-hour rhythm it creates governs life on Earth, from the daily cycles of photosynthesis in plants to the sleep-wake, patterns of animals to human schedules and societies. We take it for granted, this turning of the world, yet it is one of the most fundamental motions in our immediate cosmic environment, shaping time itself as we experience it. The aurora borealis and aurora australis are among the most beautiful phenomena visible from Earth's surface, and from space, they offer a different spectacle entirely. Astronauts aboard the International Space Station often find themselves at the same altitude as the aurora, sometimes even above it, looking down on the shimmering curtains of light as they drape across Earth's polar regions. Auroras occur when charged particles from the Sun, primarily electrons and protons, collide with atoms and molecules in Earth's upper atmosphere. These particles are guided toward the poles by Earth's magnetic field, funneling into the polar cusps where the magnetic field lines dive down toward the surface. When a high-energy electron strikes an oxygen or nitrogen atom in the thermosphere or mesosphere, it transfers energy to that atom, exciting its electrons to higher energy states. When the electrons drop back to their normal states, they release that energy as light. The altitude at which collisions occur determines the color. Green auroras, the most common variety, are produced by oxygen atoms at altitudes between about 60 and 150 miles. At these heights, collisions are frequent enough that excited oxygen atoms release their energy as light within a fraction of a second, creating the characteristic green glow. Red auroras occur at higher altitudes, above 150 miles, where the atmosphere is thinner and collisions are less frequent. Here, excited oxygen atoms can remain in their higher energy state for up to 2 minutes before emitting light, and the emitted photons are red rather than green. Blue and purple hues in auroras are produced by nitrogen. Molecular nitrogen emits blue light when ionized, meaning when one of its electrons is knocked completely free. Neutral nitrogen molecules emit purple or red light when excited. These colors typically appear at the lower edges of auroral displays at altitudes below about 60 miles, where the atmospheric density is high enough for nitrogen to play a more prominent role. From the International Space Station's perspective, auroras often appear as glowing curtains extending below the spacecraft. The station orbits at an altitude of about 254 miles, well above the peak altitude where most auroral light is emitted. Astronauts can photograph the aurora from above or from the side, capturing its vertical structure and extent. The curtains can stretch for hundreds or even thousands of miles along Earth's surface, following the oval-shaped auroral zones that surround the magnetic poles. The auroral zones are not centered on the geographic poles, but on the magnetic poles, which are offset from the geographic poles and drift slowly over time. The North Magnetic Pole is currently located in the Canadian Arctic, several hundred miles from the geographic North Pole. As a result, the aurora borealis is most commonly visible from northern Canada, Alaska, Scandinavia, and northern Russia, rather than from Greenland, which lies closer to the geographic pole but farther from the magnetic pole. The intensity and extent of auroras vary with solar activity. During solar maximum, when the sun's magnetic field is most active and sunspots are numerous, coronal mass ejections and solar flares are more frequent, sending powerful bursts of plasma toward Earth. When these plasma clouds strike Earth's magnetosphere, they compress it, transferring energy into the system and triggering geomagnetic storms. During these storms, auroras can be visible at much lower latitudes than usual. Historical records describe auroras seen from the Caribbean, Hawaii, and even near the equator during the most extreme solar storms. The solar wind itself is continuous, but its density and speed vary. During quiet periods, the solar wind carries about 5 to 10 protons per cubic centimeter past Earth's orbit at speeds of roughly 250 to 500 miles per second. During coronal mass ejections, these values can increase dramatically, with particle densities reaching hundreds per cubic centimeter and speeds exceeding 1,000 miles per second. When such a fast, dense plasma cloud hits Earth's magnetosphere, the impact creates a shock wave, accelerating particles already trapped in the magnetosphere and injecting new particles into the system. These energized particles precipitate into the atmosphere along magnetic field lines, creating bright, dynamic auroras. Aurora displays can change rapidly, with curtains of light rippling and pulsing in response to changing conditions in the magnetosphere. From the ground, observers see these curtains as vertical structures extending from the horizon upward into the sky. From space, the view is reversed. The aurora is below, a glowing band of green or red draped across the dark surface of the polar regions with stars visible above. The aurora is not the only light show in the polar regions. Polar stratospheric clouds, also called nacreous clouds, can form in the extremely cold stratosphere during the polar winter. These clouds are composed of tiny ice crystals and can create brilliant iridescent displays of color when illuminated by sunlight, even when the surface below is in darkness. From space, these clouds are less dramatic than auroras, but add another layer of color and light to the polar atmosphere. The auroral zones are roughly circular bands extending from about 60 to 75 degrees latitude around each magnetic pole. Within these zones, auroras are visible on most clear nights, though their brightness and extent vary. Outside these zones, auroras are less common and typically require enhanced solar activity to be visible. The zones expand and contract depending on geomagnetic activity. During major storms, they can extend to 40 degrees latitude or even lower, bringing the aurora to regions where it is normally never seen. From the International Space Station, astronauts have captured time-lapse sequences showing auroras evolving over minutes to hours. The curtains shift and flow, sometimes appearing almost static, other times dancing and pulsating with remarkable speed. The motion reflects changes in the magnetosphere as it responds to fluctuations in the solar wind and releases stored magnetic energy. These releases can occur suddenly, creating bright, active auroras called substorms that last for minutes to hours before subsiding. The height of the aurora makes it visible from enormous distances. An aurora located above northern Canada can be seen from locations more than 1,000 miles away if the observer has a clear view toward the northern horizon. From the International Space Station, which orbits much higher, auroras can be visible from even greater distances, appearing as faint glows along the limb of Earth when the station is far from the polar regions. The energy involved in a large auroral display is substantial. A typical auroral display releases energy at a rate comparable to a large terrestrial power plant, around 1 billion watts. During major geomagnetic storms, the total power dissipated in the auroral zones can reach trillions of watts, comparable to the total electrical generating capacity of human civilization. This energy is ultimately derived from the solar wind and Earth's magnetic field, converted through a complex series of processes in the magnetosphere and ionosphere into the kinetic energy of particles that then collide with atmospheric atoms and create light. Despite this energy, the aurora is remarkably diffuse and dim compared to artificial light sources. Individual photons are emitted by atoms scattered throughout a larger volume of the upper atmosphere, creating a glow that is spread over thousands of square miles. The light is faint enough that it does not appreciably heat the atmosphere below or have any significant effect on weather or climate. It is purely a visual phenomenon, beautiful and ephemeral, a visible manifestation of the interaction between Earth and the Sun. To see Earth as a complete sphere, you must be at least 7,000 miles above its surface. This is approximately 1/10 of the distance from Earth to the Moon. From the International Space Station at 254 miles up, Earth appears as a wide arc that extends beyond the window frames, too large to take in all at once. You can see hundreds of miles of coastline, multiple countries, vast stretches of ocean, but you cannot see the whole planet. The curvature is apparent, but you are still too close to perceive Earth as a sphere floating in space. The first humans to see Earth as a whole were the astronauts of Apollo 8, who orbited the Moon in December 1968. From a distance of roughly 240,000 miles, Earth appeared as a small blue and white sphere, suspended in the blackness of space. The photograph they took, showing Earth rising above the Moon's barren gray horizon, became one of the most iconic images of the 20th century. It revealed our planet as a finite, isolated object, beautiful and fragile, with no visible borders or divisions. The famous blue marble photograph was taken by the crew of Apollo 17 on December 7, 1972, from a distance of about 28,000 miles. At this distance, Earth appeared as a perfect sphere, fully illuminated by the sun because the spacecraft was positioned such that the sun was behind the astronauts, shining directly onto the hemisphere of Earth facing them. Africa and the Antarctic ice sheet were prominently visible, along with swirling clouds over the Indian Ocean and the blue of the Atlantic. The photograph showed Earth in a way that no one had seen before, as a single, unified world suspended in the void. From this distance, individual countries are invisible. Borders exist only in our minds and on our maps. What is visible are the natural features: continents shaped by plate tectonics, oceans filling the basins between them, ice caps gleaming white at the poles, clouds marking weather systems, deserts appearing brown and barren, forests showing as patches of dark green. These are the features that define Earth from space, the result of physical and biological processes operating over geological timescales. At even greater distances, Earth shrinks further. The Voyager 1 spacecraft, launched in 1977, took a photograph of Earth from beyond the orbit of Neptune in 1990 at a distance of about 3.7 billion miles. In that image, Earth appears as a pale blue dot, less than 1 pixel in size, almost lost against the vastness of space. The photograph, suggested by astronomer Carl Sagan, became a profound reminder of Earth's insignificance in the cosmic scale. That tiny point of light contains all human history, every person who has ever lived, every civilization that has risen and fallen, all contained within a speck too small to show any detail. From such distances, Earth's atmosphere is invisible. Its oceans, clouds, continents, all are compressed into a single point of light. The planet's color, a pale blue, is the only indication that this is Earth rather than any other rocky world. That blue comes from our ocean and atmosphere, features that make Earth unique among the planets we have explored. Mars appears red due to iron oxide in its soil. Venus appears bright white due to its thick clouds of sulfuric acid. Jupiter and Saturn show bands of color from their complex atmospheres. But Earth is blue, the color of life, of water, of an atmosphere rich in oxygen. The perspective changes everything. From the surface, Earth seems immense, almost infinite. We can travel for days or weeks without reaching the horizon we set out toward. Mountains tower above us, oceans stretch beyond our vision, the sky extends overhead, seemingly limitless. But from space, Earth is revealed as small and bounded. The atmosphere is a thin shell. The oceans are puddles spread across the surface. The mountains are barely visible wrinkles. The planet entire is a finite sphere of rock and metal and water, one world among countless others. This perspective shift is often called the overview effect, a term coined by author Frank White to describe the cognitive shift that astronauts experience when seeing Earth from space. Many astronauts report that the experience changed their understanding of humanity and our place in the universe. The borders that divide nations seemed arbitrary and meaningless. The conflicts that dominate human affairs appeared trivial when viewed against the backdrop of the cosmos. Earth appeared fragile, a delicate oasis of life and warmth in the cold darkness of space. From the Moon, Earth subtends an angle of about 2 degrees in the sky, roughly 4 times the apparent size of the full moon as seen from Earth. It appears large and bright, a blue and white ornament hanging in the black sky. The moon has no atmosphere, so there is no blue sky to compete with Earth's light, no scattering to wash out its appearance. Earth simply hangs there, unchanging in position because the moon is tidally locked, always showing the same face to Earth. Astronauts on the moon's surface would see Earth rotate slowly, showing different continents and oceans as the hours passed, but Earth would remain in the same position in the sky, never rising or setting. From Mars, Earth would appear as a bright star, sometimes visible in the morning or evening sky, depending on the relative positions of the 2 planets in their orbits. Through a telescope, Earth and the Moon would be visible as 2 separate points of light, a double star unique in the Martian sky. The Moon would appear to orbit Earth, completing 1 circuit roughly every month. Any hypothetical observer on Mars would see our blue world as we see Venus from Earth, a bright morning or evening star, occasionally passing close to the Sun in Mars's sky, but never straying too far from it. From the outer planets, Earth is lost in the Sun's glare. Jupiter, Saturn, Uranus, Neptune. These worlds are so far from the Sun that Earth orbits deep within the Sun's corona as seen from their distance. Only from very specific positions in their orbits, when Earth is at maximum angular separation from the Sun, could a telescope possibly glimpse our planet. And even then, Earth would appear as an insignificant point, one more planet among several visible near the distant Sun. From interstellar space, from the distances between stars, Earth is utterly invisible. The Sun itself appears as just another star, perhaps slightly brighter than average, but nothing to distinguish it from billions of others. Our entire solar system, all its planets and moons and asteroids and comets, would be invisible, compressed into the single point of light that is our Sun. Any alien civilization looking at our Sun from light years away would have no indication that life existed here. They would need extraordinarily sensitive instruments to detect the planets at all, and even more sophisticated technology to analyze those planets' atmospheres and search for signs of biology. Yet, from our perspective here, Earth fills our entire existence. It is our home, the only world we have ever known. The shift in perspective that comes from seeing it whole, from understanding our place in space, does not diminish our connection to it. If anything, it strengthens that connection, revealing Earth as precious and irreplaceable, the only known haven for life in a cosmos that is vast and largely empty. Earth is sometimes described as a single integrated system, and from space, this integration is visible. The atmosphere, ocean, land, ice, and living organisms all interact in complex ways, exchanging energy, water, and chemical elements in cycles that maintain the conditions suitable for life. The climate system is driven by uneven heating of Earth's surface by the Sun. The tropics receive more solar energy per unit area than the poles because sunlight strikes the surface more directly near the equator. This creates a temperature gradient from equator to pole, and this gradient drives atmospheric and ocean circulation as heat is transported from warm regions toward cold regions. In the atmosphere, warm air rises near the equator, creating a zone of low pressure and frequent precipitation. This rising air moves poleward at high altitudes, cools, and descends around 30 degrees north and south latitude, creating subtropical high-pressure zones. Some of this descending air returns toward the equator at low altitudes, forming the trade winds, while some continues poleward, creating mid-latitude westerlies. This creates 3 circulation cells in each hemisphere: the Hadley cell between the equator and 30 degrees, the Ferrel cell between 30 and 60 degrees, and the polar cell between 60 degrees and the pole. From space, these circulation patterns are visible in the cloud distributions. The intertropical convergence zone appears as a band of clouds encircling the planet near the equator. The subtropical high-pressure zones appear as relatively cloud-free regions, though not completely clear. The mid-latitudes show frequent weather systems, with spiraling clouds marking low-pressure centers and fronts. The polar regions show different cloud patterns, often with smaller-scale features and ice-covered surfaces that reflect much of the incoming sunlight back to space. The ocean plays a critical role in regulating climate by storing and transporting heat. Water has a high heat capacity, meaning it can absorb large amounts of energy without experiencing large temperature changes. The ocean absorbs about 90% of the excess heat trapped by greenhouse gases, moderating the rate of surface warming that would otherwise occur. Ocean currents transport this heat around the globe, warming some regions and cooling others. The thermohaline circulation, also called the global ocean conveyor belt, is a large-scale circulation driven by differences in temperature and salinity. Dense, cold, salty water sinks in the North Atlantic and flows southward at depth, eventually reaching the Southern Ocean and upwelling in the Indian and Pacific Oceans. This deep water gradually warms and rises, then flows back toward the Atlantic at the surface, completing a circuit that takes about 1,000 years. This circulation transports heat and helps distribute dissolved oxygen and nutrients throughout the deep ocean. From orbit, the ocean surface appears deceptively simple, but beneath that surface, currents flow in complex three-dimensional patterns. Some currents, like the Gulf Stream and the Kuroshio Current, are visible from space through their effects on sea surface temperature. Satellites equipped with infrared sensors can map these temperature patterns, revealing the boundaries between water masses and the swirling eddies that form when currents become unstable. The cryosphere, all the ice on Earth, is another critical component of the climate system. Ice and snow reflect 70 to 90% of incoming solar radiation, compared to the ocean, which reflects only about 6%. This makes ice a powerful influence on climate. When ice expands, it reflects more sunlight, cooling the climate further and potentially leading to more ice growth. This is called ice albedo feedback, and it can amplify cooling trends. Conversely, when ice melts, it exposes darker surfaces that absorb more sunlight, warming the climate further and potentially accelerating ice loss. Arctic sea ice reaches its minimum extent in September each year after a summer of melting, and its maximum extent in March after a winter of growth. Antarctic sea ice follows the opposite cycle, reaching maximum in September and minimum in February. The two regions behave differently because the Arctic is an ocean surrounded by continents, while Antarctica is a continent surrounded by ocean. This affects how ice forms, drifts, and melts. Land surfaces also play a role in climate. Vegetation absorbs carbon dioxide from the atmosphere during photosynthesis, storing carbon in plant tissues and soils. Forests, grasslands, wetlands, and croplands all influence local and regional climate through their effects on water cycling, albedo, and surface roughness. From space, different vegetation types are distinguishable by their color and reflectance properties. Satellites equipped with multispectral sensors can map vegetation health, photosynthetic activity, and land use changes over time. The biosphere, all living things, is both influenced by and influences climate. Plants absorb carbon dioxide and release oxygen, altering atmospheric composition. Phytoplankton in the ocean do the same on a massive scale. Animals and microorganisms decompose organic matter, releasing carbon dioxide back to the atmosphere and soil. These biological processes have operated for billions of years, gradually transforming Earth's atmosphere from a carbon dioxide-rich environment with little oxygen to the oxygen-rich atmosphere we have today. From space, the most visible evidence of life is the green color of vegetated land surfaces and the seasonal changes in that color as plants respond to varying sunlight and temperature. In temperate regions, vegetation greens in spring as leaves emerge, reaches peak greenness in summer, and fades in autumn as leaves fall. This seasonal cycle is synchronized with Earth's orbit and its axial tilt, which creates the varying day length and solar angle that drive the seasons. The carbon cycle connects the atmosphere, ocean, land, and living organisms. Carbon dioxide dissolves in seawater, where it can be taken up by phytoplankton and converted into organic matter. Some of this organic matter sinks to the deep ocean when organisms die, effectively removing carbon from the surface ocean and atmosphere for long periods. On land, plants absorb carbon dioxide through photosynthesis and store it in wood and leaves. When plants die and decay, Some of this carbon returns to the atmosphere, while some is incorporated into soils where it can remain for centuries. Volcanic eruptions release carbon dioxide that has been stored in Earth's interior, adding it to the atmosphere over geological timescales. Weathering of rocks gradually removes carbon dioxide from the atmosphere as carbon reacts with minerals and is carried to the ocean by rivers, where it eventually forms carbonate sediments on the ocean floor. These sediments can be subducted into the mantle at tectonic plate boundaries, completing the cycle by returning carbon to the interior, where it can eventually be released by future volcanism. All these systems operate simultaneously, interacting in ways that are still not fully understood despite decades of study. Earth is not a simple system with a single equilibrium state. It is complex, nonlinear, capable of abrupt changes and tipping points. The climate system has undergone dramatic shifts throughout Earth's history, from ice ages when ice sheets covered much of the continents to hothouse periods when the poles were free of ice and tropical conditions extended to high latitudes. From space, you can see some of these systems operating in real time. You can watch weather systems develop and dissipate. You can observe seasonal changes in ice cover, vegetation, and snow. You can see dust storms in the Sahara, smoke from wildfires, algae, blooms in the ocean, volcanic plumes spreading across the sky. All of this reveals Earth as dynamic, constantly changing, shaped by the interaction of physical, chemical, and biological processes. Yet, despite this dynamism, the overall system maintains conditions remarkably stable over long periods. For billions of years, Earth has remained habitable, with liquid water on its surface and temperatures in a range suitable for life. This stability is sometimes called the Gaia hypothesis, the idea that life itself helps regulate Earth's environment, though this remains a topic of scientific debate. Whether or not life actively regulates the planet, it is clear that living organisms are deeply integrated into Earth's systems, influencing and being influenced by the flows of energy and matter that shape our world. Earth's atmosphere contains layers of airglow that become visible from orbit during the night. This airglow is produced by chemical reactions in the upper atmosphere, where sunlight absorbed during the day is slowly released as faint light after sunset. The glow is too dim to see from the ground against the brightness of the sky, but from space, it appears as a thin greenish or reddish band extending above the surface. The airglow layer reveals the dynamic nature of the upper atmosphere. It shifts and ripples in response to atmospheric waves, gravity waves that propagate vertically through the atmosphere, carrying energy from the lower atmosphere into the thermosphere. These waves can be generated by thunderstorms, mountain ranges, or the flow of air over terrain features. They are invisible from the ground but create visible patterns in the airglow layer, appearing as parallel bands or chevron shapes that move slowly across the sky when photographed from the International Space Station. At night, Earth's cities glow with artificial light, creating patterns that reveal human settlement and development. From orbit, these lights appear as clusters and networks, with bright spots marking major metropolitan areas and fainter lines tracing highways and roads. The distribution is uneven. The eastern United States and Europe are densely lit, with continuous swaths of light extending across entire regions. Parts of Asia, particularly Japan, South Korea, and eastern China, are similarly bright. In contrast, much of Africa, Central Asia, and the Amazon basin remain dark, with only scattered points of light. The color of city lights varies depending on the type of lighting used. Older sodium vapor lamps emit an orange-yellow light. Mercury vapor lamps produce a blue-green light. Newer LED streetlights can emit white light or various colors depending on their design. From space, these differences are visible, creating a patchwork of colors across urban areas. The transition from one type of lighting to another sometimes marks political or administrative boundaries, as different regions adopt different lighting technologies at different times. Lightning illuminates clouds from within, appearing as bright flashes scattered across the dark continents and oceans. Thunderstorms can be tracked by their lightning activity, with particularly intense storms producing hundreds of flashes per hour. From orbit, these flashes are visible even during the day, though they are far more dramatic at night when they stand out against the darkness. The Earth's magnetic field creates a bow shock in the solar wind, similar to the bow wave created by a boat moving through water. Upstream of this shock, the solar wind flows smoothly past Earth's magnetosphere. Downstream, the flow is turbulent and compressed. The magnetopause, the boundary between the solar wind and the magnetosphere, is a dynamic region where plasma waves and instabilities create complex structures. These are invisible to the naked eye, but can be mapped by satellites equipped with instruments to measure magnetic fields and charged particles. The radiation belts, discovered in the late 1950s, are regions where charged particles become trapped in Earth's magnetic field. These particles spiral along magnetic field lines, bouncing between the north and south magnetic poles. The inner belt contains primarily protons, while the outer belt contains primarily electrons. Between the two belts is a slot region where particle densities are much lower, though the exact structure varies depending on solar activity and other factors. During geomagnetic storms, when coronal mass ejections from the Sun impact Earth's magnetosphere, the radiation belts can change dramatically. Additional particles are injected into the system, increasing radiation levels. The belts can expand or contract. New temporary belts can form and then dissipate as the storm subsides. These changes pose hazards to satellites, which must be designed to withstand the radiation environment or use shielding to protect sensitive electronics. Earth's surface features are shaped by plate tectonics, the slow movement of the planet's outer shell. The crust is broken into numerous plates that move at rates ranging from about 10 to 160 millimeters per year, roughly the speed at which fingernails or hair grow. The Americas are separating from Europe and Africa at approximately 25 millimeters per year, a pace so slow that it accumulates to meaningful distances only over millions of years. These plates ride on the partially molten asthenosphere beneath them, driven by convection currents in Earth's mantle. Heat from radioactive decay in the core and mantle creates these currents, with hot material rising, spreading horizontally beneath the crust, cooling, and then sinking back down to be reheated. This cycle drives the motion of the plates above, though the exact mechanisms remain an area of active research. Plate boundaries are where the most dramatic geological activity occurs. At divergent boundaries, plates move apart and new crust is created. The Mid-Atlantic Ridge is a classic example, a massive underwater mountain range where the North American and Eurasian plates are separating, and where volcanic activity creates new oceanic crust. At convergent boundaries, plates collide, and one typically slides beneath the other in a process called subduction. The Pacific Plate is subducting beneath several other plates around the Pacific Rim, creating the volcanoes and deep ocean trenches that characterize the region. At transform boundaries, plates slide past each other horizontally, creating earthquakes but little vertical displacement. The San Andreas Fault in California is perhaps the most famous transform boundary. From space, many of these plate boundary features are visible. The East African Rift Valley, where the African plate is slowly splitting in two, appears as a series of long valleys and lakes visible from orbit. The Himalayan mountain range, created by the collision of the Indian and Eurasian plates, stands out as a massive wrinkle in Earth's crust, with peaks covered in permanent snow and ice. The volcanic arcs of the Pacific, including Japan, the Philippines, and Indonesia, appear as chains of islands tracing the locations where subduction is occurring. The movement of these plates has shaped Earth's geography throughout its history. About 300 million years ago, all the continents were joined into a single supercontinent called Pangaea. This landmass began breaking apart around 200 million years ago, and the fragments have been drifting apart ever since, creating the configuration of continents we see today. The Atlantic Ocean formed as the Americas separated from Europe and Africa. India drifted northward and collided with Asia, creating the Himalayas. Australia separated from Antarctica and moved north toward its current position near the equator. This process continues today and will shape Earth's future geography. Simulations suggest that in approximately 250 million years, the continents may reassemble into a new supercontinent, sometimes called Pangaea Proxima. Africa is predicted to collide with Europe, potentially creating a mountain range rivaling the Himalayas. The Atlantic Ocean may close as the Americas move back toward Europe and Africa, though these predictions carry considerable uncertainty given the long timescales involved. From orbit, the evidence of past plate movements is visible in the shapes of coastlines and the distribution of mountain ranges. The matching shapes of South America's east coast and Africa's west coast, noticed by early geologists, reveal their ancient connection. The ring of volcanoes circling the Pacific Ocean, known as the Ring of Fire, marks the boundaries where oceanic plates are subducting beneath continental plates, creating the earthquakes and volcanic eruptions that characterize the region. Time moves differently when viewed from space. On Earth's surface, we experience change, constantly. Days turn to night, seasons shift, weather patterns evolve hour by hour. But from orbit, these changes appear against a backdrop of remarkable stability. The continents occupy the same positions they did yesterday and will tomorrow. The ocean basins hold the same water. The atmosphere wraps the planet in its familiar blue haze, yet change is occurring on every timescale. Earth rotates once each day, creating the rhythm of day and night that governs life on the surface. The planet orbits the Sun once each year, creating the seasons that drive annual cycles of temperature, precipitation, and biological activity. The Moon orbits Earth once each month, creating tides that rise and fall in a predictable rhythm. These cycles nest within each other, creating patterns that repeat endlessly. On longer timescales, the changes become more apparent. The climate varies over decades and centuries, influenced by ocean circulation patterns, solar activity, volcanic eruptions, and atmospheric composition. Ice sheets expand and contract over tens of thousands of years, driven by subtle changes in Earth's orbit and axial tilt. Continents drift apart or collide over tens of millions of years, reshaping Earth's surface geography. Stars slowly shift their positions over thousands of years as Earth's rotational axis precesses. From the International Space Station, the most visible changes occur on human timescales. Astronauts can watch hurricanes develop and intensify, seeing cloud patterns evolve from disorganized clusters into organized spiral systems over the course of days. They can observe ice breaking up in polar regions during spring, large sheets fragmenting into smaller pieces that drift with currents and winds. They can see seasonal changes in vegetation, watching the northern forests green up in spring and lose their leaves in autumn. Night and day create the most regular cycle visible from orbit. The Terminator sweeps across the surface at roughly 1,000 miles per hour at the equator, though its speed varies with latitude. Cities light up as they enter night. their illumination revealing population centers and transportation networks. Agricultural fires in tropical regions become visible, tiny bright points scattered across otherwise dark landscapes. Lightning in thunderstorms creates flickering lights visible for hundreds of miles. The atmosphere is in constant motion, though the overall pattern remains recognizable. Weather systems develop, intensify, and dissipate over periods of days to weeks. Clouds form and dissolve. Winds blow, carrying moisture from the ocean to the land, where it falls as rain or snow and then flows back to the ocean through rivers and streams. This cycle has operated for billions of years, moving the same water molecules through the system repeatedly. Earth's magnetic field quietly performs its protective function, deflecting the solar wind and allowing the atmosphere to persist. Auroras shimmer. Near the poles, visible evidence of this interaction between Earth and the Sun. The magnetosphere flexes and responds to changing solar conditions, sometimes compressed by strong solar winds, other times expanding outward when solar activity is quiet. These variations occur on timescales of minutes to days, too fast to perceive directly but measurable by satellites and visible through their effects on auroral displays. Life continues its processes on the surface below. Plants photosynthesize, converting sunlight, water, and carbon dioxide into organic matter and oxygen. Animals breathe that oxygen and exhale carbon dioxide, completing the cycle. Microorganisms decompose dead organic matter, returning nutrients to the soil. The ocean teems with phytoplankton and zooplankton, fish and whales, all part of interconnected food webs that have evolved over hundreds of millions of years. From space, individual organisms are invisible, but their collective effects are not. Seasonal changes. In vegetation, color reflect the annual cycle of plant growth and dormancy in temperate regions. Phytoplankton blooms create swirls of green and turquoise in the ocean. Wildfires, though sometimes started by humans, are also a natural part of many ecosystems, and their smoke plumes are visible from hundreds of miles away. The view from orbit emphasizes Earth's isolation. Beyond the thin shell of atmosphere, there is vacuum, near emptiness extending for vast distances. The Moon orbits about 240,000 miles away, taking about 27 days to complete one orbit. It appears small from the International Space Station, not significantly larger than it does from Earth's surface. Beyond the Moon, the nearest substantial bodies are Venus and Mars, both tens of millions of miles away at their closest approaches. This isolation means Earth is a closed system for most practical purposes. Energy arrives from the Sun, but matter does not enter or leave in significant quantities. A few tons of meteoric material fall to Earth each day, and a tiny amount of hydrogen and helium escape to space, but these fluxes are negligible compared to Earth's total mass. Everything we have, all the air we breathe, all the water we drink, all the materials we use, all of it has been here for billions of years, cycling through different forms but never leaving the system. This perspective encourages a sense of responsibility. Earth is not infinitely large or infinitely resilient. It is a finite world with limited resources and limited capacity to absorb waste. The systems that make it habitable, the atmosphere, the ocean, the climate, the biosphere, all are interconnected and can be disrupted by sufficiently large disturbances. The view from space makes this clear in a way that is difficult to appreciate from the surface. Yet Earth is also remarkably stable. Life has persisted for at least 3.5 billion years, surviving asteroid impacts, volcanic eruptions, ice ages, and countless other challenges. The climate system maintains conditions suitable for life Despite variations in solar output and changes in atmospheric composition, the magnetic field has protected the atmosphere for billions of years. The water cycle continues to distribute water across the planet. The tectonic system renews the crust and regulates atmospheric carbon dioxide through the carbon cycle. This stability is not static. It is dynamic, maintained by constant flows of energy and matter through the Earth system. The Sun provides energy that drives atmospheric and ocean circulation, evaporates water, and powers photosynthesis. Heat from Earth's interior drives plate tectonics and the geodynamo that generates the magnetic field. Gravity holds the atmosphere and ocean in place and shapes the orbits of Earth and Moon. These fundamental processes have operated for eons and will continue to operate for eons to come. From the International Space Station, astronauts have described a shift in perspective called the overview effect. Seeing Earth whole, seeing it as one interconnected system, seeing the thinness of the atmosphere and the absence of visible borders, all of this creates a profound cognitive shift. The planet appears simultaneously vast and tiny, robust and fragile, familiar and alien. It is home, the only home we have ever known, yet seeing it from outside provides a perspective that transforms understanding. There is a particular quality to Earth's appearance from space that is difficult to capture in words. The planet glows with reflected sunlight, appearing far brighter than the dark background of space. The blue of the ocean and atmosphere dominates, punctuated by the white of clouds and ice, the brown and green of land surfaces. These colors are not painted on, but are the natural result of physical processes. Water absorbing red light and reflecting blue, clouds scattering all wavelengths of visible light, vegetation absorbing red and blue light for photosynthesis while reflecting green. The contrast between Earth and space is stark. Earth is bright, dynamic, full of structure and pattern. Space is dark, empty, featureless, except for the distant points of stars. This contrast emphasizes Earth's uniqueness. No other planet in our solar system looks like this. Mars is red and dry. Venus is shrouded in thick clouds that hide its surface. Jupiter and Saturn are gas giants with banded atmospheres but no solid surface. The ice giants Uranus and Neptune are pale blue or bluish-green, but lack Earth's complex surface features. Earth's appearance changes with the seasons, though these changes are most visible in temperate and polar regions. Summer in the northern hemisphere brings green to the forests and grasslands of North America, Europe, and Asia. Winter turns the same regions brown and white as vegetation goes dormant and snow covers the ground. Ice expands across the Arctic Ocean, while ice recedes in Antarctica. 6 months later, the pattern reverses as seasons switch hemispheres. The clouds are endlessly variable, yet their patterns are governed by predictable physical principles. Warm, moist air rises and cools, water vapor condenses, clouds form. The Coriolis effect causes rotating systems to develop in both hemispheres. The temperature difference between equator and poles drives atmospheric circulation. These principles create weather patterns that vary in detail but follow recognizable forms. From orbit, the human presence on Earth is evident primarily through city lights at night, though some other features are visible during the day. Agricultural land creates geometric patterns of fields that differ from the irregular shapes of natural landscapes. Large cities appear as gray patches during the day, their buildings and streets creating a different reflectance than surrounding terrain. At night, the lights reveal the extent of human settlement with remarkable clarity. Yet, even the largest cities are small features on a planetary scale. From the altitude of the International Space Station, a major metropolitan area might occupy a small portion of the visible area. From the altitude of geosynchronous satellites, 22,000 miles up, cities are barely visible points. From the distance of the Moon, they are invisible, lost in the larger features of continents and oceans. This scaling reinforces Earth's vastness from a human perspective and its smallness from a cosmic one. The planet has a diameter of nearly 8,000 miles and a surface area of about 197 million square miles. A human walking at 3 miles per hour would need more than 2,600 hours, or about 108 days of continuous walking, to circle the equator. Yet Earth is tiny compared to Jupiter, which has a diameter more than 11 times larger, or the Sun, which is more than 100 times larger in diameter. The Sun itself, from Earth's perspective, subtends an angle of about half a degree in the sky. It appears as a disk, bright enough to illuminate the entire day side of Earth, but small enough to be blocked completely by a finger held at arm's length. This modest appearance belies the Sun's true scale and power. It contains 99.86% of all the mass in the solar system. Its core reaches temperatures of about 15 million degrees Celsius, hot enough for nuclear fusion to convert hydrogen into helium, releasing the energy that lights and warms Earth. From the Sun's perspective, Earth orbits at a distance of about 93 million miles, taking 1 year to complete each orbit. This distance is called 1 astronomical unit and serves as a convenient yardstick for measuring distances within the solar system. Earth's orbit is nearly circular, varying by only about 3% between its closest and farthest points from the Sun. This near circularity helps maintain relatively stable temperatures throughout the year, with seasons driven by axial tilt rather than distance from the Sun. The Moon, Earth's only natural satellite, orbits at an average distance of about 238,855 miles. It is large for a moon relative to its planet, with a diameter about 1/4 that of Earth. This size ratio is unusual in the solar system. Most moons are much smaller relative to their parent planets. The Moon's formation likely involved a giant impact between the early Earth and a Mars-sized body, with debris from the collision coalescing to form the Moon. The Moon's gravity creates tides in Earth's ocean and to a lesser extent in the solid Earth itself. These tidal forces have gradually slowed Earth's rotation over billions of years and have also caused the Moon to recede slowly from Earth, currently at a rate of about 3.8 centimeters per year. This tidal interaction has locked the Moon's rotation to its orbit, so it always shows the same face to Earth, a configuration called tidal locking. From space, the Earth-Moon system appears as two bodies orbiting their common center of mass, though this point lies within Earth's interior due to the planet's much greater mass. They travel together around the Sun, a binary system unique in the inner solar system. The Moon's presence has likely stabilized Earth's axial tilt, preventing the chaotic variations that might otherwise occur and helping maintain the stable climate that has allowed life to flourish. Observing Earth from space has transformed our understanding of the planet in ways that extend beyond simple description. Satellites have mapped the entire surface in detail, revealing features invisible from the ground. They have measured ocean temperatures, atmospheric composition, ice extent, vegetation health, and countless other parameters, creating datasets that allow scientists to monitor changes and understand processes operating at global scales. The first weather satellites, launched in the 1960s, provided the first continuous views of cloud patterns across entire hemispheres. For the first time, meteorologists could see hurricanes from formation to dissipation, could track fronts and storms as they moved across continents and oceans. This revolutionized weather forecasting, allowing predictions days in advance rather than just hours. Later, satellites added instruments to measure other parameters. Radar altimeters measure sea surface height, revealing ocean currents and variability. Infrared sensors measure temperature at the surface and throughout the atmosphere. Microwave sensors penetrate clouds to measure precipitation. Spectrometers analyze the light reflected or emitted by the surface to determine composition, identifying minerals, vegetation types, water quality, and atmospheric gases. The Landsat program, begun in 1972, has provided continuous monitoring of land surfaces for more than 5 decades, creating an archive that allows scientists to track deforestation, urban expansion, agricultural development, glacial retreat, and countless other changes over time. These observations have documented the pace and extent of human modification of Earth's surface with unprecedented clarity. Earth-observing satellites have also revealed phenomena that were unknown or poorly understood before the space age. The Antarctic ozone hole was discovered through satellite observations in the 1980s, showing seasonal depletion of stratospheric ozone over Antarctica caused by human-produced chlorofluorocarbons. This discovery led to international agreements to phase out these chemicals, and the ozone layer has shown signs of recovery in recent years. Satellites have mapped the ocean floor using gravity measurements, revealing underwater mountains, trenches, and the entire global system of mid-ocean ridges where new crust is created. They have measured tiny variations in Earth's gravitational field, revealing mass anomalies that reflect differences in the thickness and density of Earth's crust and mantle. They have tracked changes in ice sheets and glaciers, documenting the acceleration of ice loss in Greenland and parts of Antarctica. The view from space has also provided context for Earth's place in the solar system and beyond. By observing how Earth appears from different distances and comparing it to other planets, we gain perspective on what makes our world unique. The presence of liquid water, the oxygen-rich atmosphere, the moderate temperatures, the active geology, all of these features distinguish Earth from other known planets. The search for exoplanets, planets orbiting other stars, has been remarkably successful in recent decades, with thousands of confirmed discoveries. Many of these planets are nothing like Earth, hot Jupiters orbiting close to their stars, super-Earths several times more massive than our planet, planets in binary star systems, or orbiting dead stars. Yet occasionally, astronomers find planets in the habitable zones of their stars where temperatures might allow liquid water to exist. Whether any of these planets actually harbor life remains unknown, but the search continues. The perspective gained from seeing Earth from space emphasizes both its uniqueness and its fragility. It is the only known planet with life, the only known place in the cosmos where biological processes have transformed the surface and atmosphere. Yet, it is also a small world, with finite resources and limited capacity to absorb disturbances. The systems that maintain habitability operate within narrow ranges, and pushing them too far could trigger changes that would be difficult or impossible to reverse on human timescales. This knowledge creates a responsibility to understand Earth's systems and to make decisions informed by that understanding. The view from space provides data and context that can guide these decisions, revealing connections between human activities and planetary scale changes, showing which systems are most vulnerable and which are most resilient. Yet there is also a sense of wonder in seeing Earth from this perspective. The planet is beautiful, its swirling clouds and blue oceans creating patterns that are endlessly varied, yet somehow harmonious. The terminator dividing day from night, the aurora shimmering near the poles, the sun glinting off the ocean surface. These sites remind us that Earth is not just a collection of resources to be managed, but a world to be appreciated, a home to be cherished. Earth continues its rotation, carrying the day-night boundary across continents and oceans, bringing sunrise to some places while others enter the darkness of night. The atmosphere flows, redistributing heat and moisture, creating weather that varies from place to place but follows patterns shaped by fundamental physical principles. The ocean circulates, mixing warm and cold water, carrying nutrients from deep to shallow, supporting ecosystems from microscopic plankton to the largest whales. The magnetic field surrounds the planet, invisible yet essential, deflecting the solar wind and allowing the atmosphere to persist. Auroras dance near the poles when solar activity increases, their green and red light revealing the interaction between Earth and Sun. Clouds drift across the sky, their shapes and motions reflecting the state of the atmosphere, their presence moderating temperatures and distributing fresh water across the land. From the International Space Station, astronauts continue their work, conducting experiments, maintaining systems, occasionally taking time to look out the windows at the planet below. They see Earth as few humans have, whole and complete. A sphere of blue and white and brown and green, suspended in the blackness of space. They see it turn beneath them 15 times, each day showing different faces, different continents, different weather systems, yet always recognizable as home. The perspective from space reveals Earth's systems operating simultaneously at every scale. Atoms and molecules collide in the atmosphere, exchanging energy and creating the properties of air. Clouds form and dissipate, covering hundreds of square miles. Weather systems develop and move, influencing climate across continents. The ocean circulates globally, transporting heat from equator to poles. Plates drift slowly, reshaping continents over millions of years. All of these processes occur simultaneously, interconnected through flows of energy and matter. This complexity is the result of 4.5 billion years of planetary evolution. Earth formed from the gravitational collapse of a cloud of gas and dust, along with the Sun and other planets. It differentiated into core, mantle, and crust as heavy elements sank and light elements rose. It was bombarded by asteroids and comets, which delivered water and organic molecules. Its atmosphere evolved through volcanic outgassing, escape of light gases, and eventually the rise of photosynthetic life that added oxygen. Life itself has profoundly shaped Earth. Photosynthetic organisms transformed the atmosphere from carbon dioxide-rich to oxygen-rich. Their remains formed vast deposits of coal, oil, and gas. They created soils through their activity and their decomposition. They influenced climate through their effects on atmospheric composition and surface properties. They filled every available habitat, from the deepest ocean trenches to the highest mountain peaks, from frozen polar regions to scorching deserts. And now, from orbit, we can see the result of all this history, all this evolution, all these interconnected processes operating together. We see a living planet, dynamic yet stable, complex yet comprehensible, beautiful yet functional. We see our home, the only world we have ever known, the only place in the universe confirmed to harbor life. This view from space is a gift, a perspective that previous generations could only imagine. It reveals Earth's systems with clarity impossible from the surface. It shows connections between distant regions, between ocean and atmosphere, between land and sea. It makes visible the thinness of the atmosphere, the vastness of the ocean, the intricate patterns of clouds and weather. It provides data that informs our understanding and guides our decisions. But perhaps most importantly, it inspires wonder. Seeing Earth whole, seeing it glow against the darkness of space, seeing the aurora shimmer and the clouds swirl and the continents drift slowly beneath, all of this creates a profound appreciation for the planet that sustains us. It reminds us that we are part of something larger, that our lives unfold on a stage shaped by forces both vast and intimate, that the blue sphere floating in space is precious and worth protecting. The view endures. Earth continues its endless rotation, its orbit around the Sun, its journey through space as part of the solar system, which itself orbits the center of the Milky Way galaxy. The perspective from above remains available to those who venture into orbit, offering its unique combination of distance and intimacy, objectivity and connection. It is a view that transforms understanding, that shifts perspective, that reminds us of our place in the cosmos and our responsibility to this small, beautiful world we call home. Thank you for joining this quiet journey through the facts of Earth as seen from space. If you found this exploration calming and informative, consider subscribing to Nebula Nights. We create these long-form science-based journeys through space and astronomy designed to inform, inspire, and perhaps help you drift peacefully towards sleep. Each video brings together verified research and gentle narration, offering you a window into the cosmos from the comfort of wherever you choose to listen. Subscribe to continue exploring the universe with us, one peaceful fact at a time.